Okay, still on dimension of deriving the dimensions of derived quantities. I have inductance. Inductance, the unit is L, and the dimension of inductance. How do we derive it? From the definition, the potential difference, that's the self-induced EMF, is given by L times I, that's current over time. Okay, so that inductance is now giving us potential difference times time divided by the current. So the dimension of potential difference, we've done that before. That gives me m L squared time t raised to the power minus 3 and I, current, raised to the power minus 1. Then divided by, multiplied by t, which is the time, that is this time, over current I. So that means the dimension of inductance, if you simplify that further using your law of indices, you have L squared. Now this is t raised to the power 1 multiplied by t raised to the power minus 3. You simplify to t raised to the power minus 2. Then this is I raised to the power minus 2. Okay, this gives the dimension of inductance. Now, dimension of permeability. Permeability, that is mu, is the symbol. Permeability has to do with magnetic field and magnetism. Okay, so the unit of permeability is Henry per meter. The unit of inductance is Henry. So this is also the dimension of the Henry unit of inductance. You can have inductance of 2 Henry, 5 Henry, 3 Henry. Okay, but this permeability, or maybe your free space or what have you, is dimension Henry per meter. So meaning that I'm going to recall or bring in this m L squared t minus 2 I minus 2 as the dimension of Henry divided by, this is length L. So that gives me m L, because this cancels one of these, t minus 2 and current raised to the power minus 2. That gives the dimension of permeability. Now let's look at the dimension of Stefan's constant. Stefan's constant. Now where is this constant used? Stefan's constant. Now I need to understand that the radiation, the energy radiated from a black body per unit surface area per unit time is directly proportional to the fourth power of temperature. Energy radiated from a black surface per unit time per unit surface area is proportional to the fourth power of temperature. So this is where Stefan constant comes in. Okay, so if I rewrite this very quickly, this is this, and I bring in my equal to sign, I have my constant proportionality, which is this. So there's another constant, but let's just work with that. That one is dimensionless. So to find the dimensions of Stefan constant, I have to make that the subject of the equation. That gives me energy, which is my E, divided by time, multiplied by area, and by the fourth power of temperature. Okay, so energy is dimension m L squared t minus 2 over time t, area L squared, temperature, you can use theta raised to the power 4, the dimension of that. So this of course we cancel out this time has the power of 1. If we divide this by this, that gives me the dimension of Stefan's constant m. Okay, that is t raised to the power minus 3 and temperature raised to the power minus 4, because when this goes up it gives you that. Some they use this k for the dimension of temperature, so you don't have this or this. Okay, that is it. So finally, let's dimension wave intensity. The intensity of a wave, the symbol is I. It is given as wave power over area. Wave intensity. Power in mechanics is given as m L raised to the power 2 t raised to the power minus 3, the dimension of power, over area, which is L raised to the power 2. So this cancels this, so that the dimension of Wave intensity is m t raised to the power minus 3. That gives the dimension of wave intensity. Okay, so I've taken a number of physical quantities, derived quantities, and then shown you how to, derive their dimensions. Now, the in thing is that you just get to know the dimensions of this separate physical quantity, because in some cases, in exam conditions, they may not just tell you to find or derive the dimension of this particular physical quantity. You may be given an equation, and the question may contain a constant, and will ask you to find the dimension of that constant. Take for instance, you have V over T equals pi times pressure radius raised to power this divided by 8 times K times L, equation of flow, where V stands for volume. No, volume, then T stands for time, P is pressure, R is radius, and then L is length. So this question will be given to you, and the examiner may ask you to find the dimensions of K. You see that? So yours is to be able to know or remember the dimensions of each of these parameters, physical quantity that appear in these equations, and then just make the equation, that is, make K the subject formula, or substitute directly the dimensions of the respective physical quantities in the equation, and then go ahead and find the dimension of K, noting that this pi and 8 are dimensionless. My first video on dimension analysis, I mentioned there are some numbers, physical quantities numbers, that are called dimensional constants. Those ones have no dimension. So when you see them in an equation like this, you just ignore them. And then making K the subject of the formula here, you have P, that's pressure, times volume raised to the power 4, multiplied by time T over um, V times L, that is volume, multiplied by length. So with this, you put in the dimension of pressure, ml minus 1, T minus 2, which means I must have the first-hand knowledge of the dimension of pressure, or else I cannot proceed with this problem. Dimension of radius, L, raised to the power 4, times T, that is multiplied by T. Dimension of volume is L3, and dimension of length is just L. So this is, product of this and this gives L4, which cancels out this one. And then you have what is left there, m. This is a raised to the power minus 1, t minus 2 multiplied by t1, that gives you t minus 1. So you have this as the dimension of K. So with the knowledge of dimensional analysis and the fact that, not all physical quantities, not all numbers, not all parameters have dimension. We have dimensionless constants. Those constants have no dimension. When you see them in equation like this, you don't consider them as part of the solution to determining the dimension of the unknown physical variable or quantity. So next video we'll look at, I'll show you the applications of dimensional analysis.